now let us consider one more example from volume integrals. This is the integral to be considered, where f is this vector field, V is the portion of the volume given by this. That means, portion of this sphere, a sphere of radius 2 centered at the origin, and also the portion in the first portion of it in the first octant. So, definitely we have to use spherical polar coordinates. So, this is the portion of the sphere of radius 2 sitting within the first octant. So, r goes from 0 to 2 in this region. Phi is this angle. If you take any like any radius of the sphere, the angle between Z and that radius. So, it will go from 0 to 5 by 2. Since we shouldn't leave the first octant, phi should be from 0 to 5 by 2. Its range is that. Then theta is this angle. Once you have this projected onto xy plane, theta is the angle between the projection and the positive direction of x axis. Since we need to stay within the first octant, theta should go from 0 to 5 by 2. You have that here. Just to recall this, the x, y and z in terms of r, phi and theta, and also the infinitesimal volume element in the context of spherical polar coordinates is this one. Now, since in the integrand we have du f, we will first find du f. This is a gradient operator with the dot product of f. So, you know I dot I is 1, therefore, you have to partially differentiate this with respect to x, you get 2x. You have to partially differentiate this guy with respect to y, it is 2x again. Then you have to partially differentiate this with respect to z, you get 2z. So, you will end up with this one. Now, if you again invoke the integral, you plug in what you have here as 4x plus 2z. Now, let us consider the spherical polar coordinates to deal with this one. Now, in the volume V, these are the limits, and this is the infinitesimal volume element. So, instead of dV, we can write that infinitesimal volume element instead of dV here, and for x, we substitute this one. For z, we have to substitute this. So, once we do that, we will end up with this integral. It is quite complicated compared to the previous ones we have considered. Now, these are the limits. You can pull out r from these two, leaving r cube outside. Now, this is what you have in the pair of parentheses. Now, when you integrate r cube, you get r to the power 4 over 4, and now you plug in limits. And remember, when you integrate with respect to r, the rest will be considered as constants. So, constant times r cube. So, you will end up with this one. Now, once you plug in limits and simplify, you get like 2 to the power 4 is 16, 16 over 4 is 4. So, you have to multiply this by 4. So, you will end up with this one. Now, it is a double integral. Now, the variable of integration is phi. So, these are the variables. So, in this level, theta is considered as a constant. Now, since you have sine squared phi, you can replace it by 1 minus cos 2 phi over 2. That 2 and 16 will get cancelled and leaving 8 like this. So, you have 1 minus cos 2 phi, cos theta will be there as it is, then you have 4 sin 2 phi. Now, phi is the variable. So, cos theta can be considered as constant. So, 8 times cos theta remained intact. Now, the integral of one is phi, integral of this one is sine 2 phi over 2. The integral of this one, the antiderivative of this one is minus 4, I mean minus 4 times minus sine cos 2 phi over 2, and these are the limits of phi. Now, in the first pair of braces, you have the value when you plug in phi by 2 minus, in the second pair of braces, you have the result when you plug in phi is equal to 0. So, this is what you get. Once you simplify it, you will end up with this one. Now, it is a simple integral. Remember, theta is the variable of integration. So, here you get 4 pi sin theta plus 4 theta. So, that is what you have here, right. From this you get this. Now, plug in the limits, you will end up with 6